Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we are jumping right into honestly, it's a microscopic battlefield.
Oh, absolutely. It's a chaotic, kind of violent environment right on the surface of a metal tube.
Right. Liquid is basically the enemy here, and
Mhm.
engineers are fighting it using, everything from microscopic sawteeth to literally 2,000 volts of raw electricity.
Yeah, it's the absolute definition of thermodynamic muddy waters. I mean, we usually think of a phase change like vapor turning into liquid as this clean binary event.
Yeah, gas to liquid, boom, done.
Right, but what actually happens when vapor meets cold metal is incredibly complex.
And that is exactly why today we are taking you on a deep dive into the fascinating, invisible, and honestly, often entirely ignored physics of condensation.
We really are getting into the weeds on this one.
For sure. We're drawing straight from this massive engineering text, Chapter 10,
Yeah.
Condensation, by M.A. Kadzierski, J.C. Chato, and T.J. Robus.
It's an exhaustive source.
Very. And our mission today is specifically for you. We want to look past the dense textbook jargon and really help you grasp the actual physical intuition behind the math of turning vapor into liquid.
Because, before we can build massive multi-million-dollar power plant condensers or optimize an industrial HVAC system, we really have to understand what happens to a single drop of water on a flat piece of metal.
Right. The microphenomena completely dictate the entire macro world.
Exactly.
So let's start with the two main ways condensation actually happens, right?
Right.
We've got film condensation and dropwise condensation.
Right.
For you listening, think about your car. Dropwise condensation is like rain perfectly beating up and rolling off a freshly waxed hood.
Yeah, that perfect bead.
Right. The drops form, they roll away, and they leave the surface completely exposed for the very next drop to form.
Mm-hmm.
But then, film condensation is like a sheet of dirty water sticking to an unwaxed windshield. It just coats the entire thing.
It's a mess.
Total. And the crazy part is, dropwise condensation is up to 100 times more efficient for heat transfer.
Which is massive.
But almost all industrial engineering relies on film condensation. So
Yeah.
I got to ask, why don't we use the method that's 100 times better?
Well, the problem really boils down to sustainability in harsh environments. Dropwise condensation requires the liquid to have basically a lack of affinity for the surface. It has to want to bead up.
Like the wax on the car.
Exactly.
Yeah.
To achieve that in a massive industrial condenser, you would have to constantly coat the metal with special promoters or polymers or noble metals.
Okay.
And in a real-world, high-temperature, high-pressure environment, those chemical coatings degrade incredibly fast.
Oh, so it just wears off.
Yeah. It is simply not economically or physically viable to maintain that perfect waxed car finish for decades. So film condensation basically becomes the default reality that engineers simply have to deal with.
We play the hand we're dealt, basically.
You do.
And the engineer who wrote the rule book on that hand was Nusselt, way back in 1916.
Oh, yeah. Nusselt's pioneering analysis of a vertical flat plate laid the foundation for, well, pretty much everything we do in this field.
Right.
But his biggest takeaway was actually a pretty sobering one for heat transfer design. He proved that the liquid film itself acts as an insulator.
Wait, the water is insulating the metal?
Yep. Water does not conduct heat nearly as well as copper or steel.
Uh-huh.
So as that continuous sheet of water flows down the plate, it gets thicker. And the thicker that film gets, the more it literally blocks the heat from escaping the vapor and getting into the cold metal.
Wow. And there's this really elegant energy equation in the text that models exactly what is happening inside that insulating film.
Right. So for a steady-state laminar film, applying Nusselt's assumptions, the energy equation reduces to this. dt divided by dy equals T subsat minus T sub W, all divided by delta.
Okay, let's unpack this.
Yeah.
Looking at those variables, what is the actual physical story playing out on the metal there?
Intuitively, it represents a thermal bottleneck. The temperature gradient, that's the dt divided by dy, is the rate at which heat moves through the liquid.
Okay.
And this movement is driven by the temperature difference between the hot saturation temperature of the vapor, which is T subsat, and the cooler wall temperature of the metal, which is T sub W.
So hot vapor, cold wall.
Exactly. But the crucial part is that this driving force is divided by delta, and delta represents the film thickness.
Oh, so it's an inverse relationship.
Right.
As delta, the film thickness, gets bigger, the entire temperature gradient drops. The heat transfer just crashes. It proves mathematically that the film is the real enemy of efficiency.
Which means your whole goal as an engineer is to keep delta as close to zero as physically possible.
But if gravity alone isn't pulling that liquid down the vertical plate fast enough, what do we actually do?
Well, we cheat.
We cheat. I love it.
We start physically shaping the metal to force the liquid off the surface way faster than gravity could ever do it alone.
Okay, so we're talking about putting fins on the outside of the tubes, but not, massive cooling fins like you'd see on an old motorcycle engine. We're talking low fins less than 1.5 millimeters tall.
Basically microscopic architecture.
Yeah.
And, most people assume fins are just there to increase the surface area because more metal equals more space for heat to transfer, right?
All right, that's what I would think.
But with condensation, these low fins serve a completely different primary purpose. They use surface tension to physically rip the liquid off the fin tips. That thins out that insulating layer right where the heat transfer is highest.
Wait, surface tension, like the exact same force that lets a water strider bug walk across a pond.
The exact same force.
How does shaping a piece of copper manipulate surface tension to physically move liquid?
It all comes down to the Laplace equation. It describes the pressure differences across a curved liquid-vapor interface. And the math here is just brilliant.
Let's hear it.
P sub L minus P sub G equals sigma times the sum of 1 divided by R sub 1 and 1 divided by R sub 2.
Okay, so sigma is the surface tension of the fluid,
Yeah.
and those R variables are the ones really doing the heavy lifting here, right?
Yeah, they are the radii of curvature of the liquid surface. The smaller the radius, meaning the tighter and sharper the curve is, the larger that whole right side of the equation becomes.
Gotcha.
And that creates a massive pressure difference between the liquid, which is P sub L, and the surrounding vapor, P sub G.
It's kind of like squeezing a long water balloon.
Oh, that's a good way to look at it.
Like, if you grab one end and squeeze it incredibly tight, creating that high curvature, the water doesn't just sit there. It is violently forced away from your hand right toward the wider, lower pressure end of the balloon.
That's exactly what's happening. By machining the fin tips to be incredibly sharp, engineers force a tight radius of curvature in the condensate film right at the tip.
Okay.
This induces a localized high pressure in the liquid, which literally sucks the condensate down into the wider troughs between the fins where the pressure is lower.
Wow.
Yeah, it constantly drains the tip, leaving a microscopically thin film, a tiny delta, like we talked about, which causes the heat transfer to just skyrocket right at the fin tip.
That's wild. And the sources actually have some real-world examples of this. They compared two commercial tubes. The turbo chill tube, which uses 2,024 trapezoidal fins per meter, and then the turbo CDI tube, which uses 1,575 sawtooth fins per meter.
Right.
And the sawtooth fins are literal sharp, notched teeth. The text says that sharp curvature of the sawtooth shape literally doubles the heat transfer performance compared to the trapezoidal one, just by making the metal sharper.
It's amazing, but what's fascinating here is that as an engineer, you need a way to know if this surface tension trick is actually going to work for a specific fin size, or if gravity is just going to overpower it anyway.
Right.
And to calculate that tug of war, we use the Bond number.
The Bond number, right? So Bond number, or BD, equals the difference between rho sub L and rho sub G times e to the power of 2, all divided by sigma times theta sub m.
Exactly. And the key takeaway for you as a designer is the result here. If the Bond number is less than 1, surface tension dominates gravity. Looking at the math, you achieve a Bond number of less than 1 by having a small fin height, that's the E term, and a large fin angle, the theta submean term. So small, sharp fins give you strong pressure gradients that totally defeat gravity.
Okay, here's where it gets really interesting. We've sculpted the metal into microscopic saw teeth to, manipulate surface tension. But what if we just abandon the metal sculpting entirely? What if we blast the tube with an electric field instead?
Electrohydrodynamic enhancement, AHD.
Yes. The text outlines using a high-voltage, low-current electric field to literally blast the condensate film off the surface of the tube.
I mean, it sounds like complete science fiction, but the physics are highly effective. You have to keep in mind it only works on fluids that have very low electrical conductivity.
Oh.
If you tried this with regular water, it would immediately short out. But it works beautifully with refrigerants.
The numbers in the research are just staggering. Beloga achieved a massive 2,000% enhancement on a plate.
It's unreal.
2,000%. The electricity rips the liquid off the surface so violently that it creates this pseudo-dropwise condensation?
Hmm.
It artificially tears that continuous film into discrete drops. But wait, hold on.
Yeah.
If blasting tubes with 2,000 volts gives us a 2,000% efficiency boost, why isn't the air conditioning unit sitting outside my bedroom window electrified right now?
It's a fair question, but it really comes down to manufacturing practicality and cost. I mean, you can't just plug the tube into a wall. It requires really complex electrodes.
Ah, okay.
Yeah, you have to wrap a highly calibrated screen around the outside of the tube, spaced at an exact distance, to generate the electric field without arcing. Or, if you're enhancing the inside of the tube, you have to run a straight rod electrode perfectly suspended down the center.
That sounds like a nightmare for an assembly line.
It adds massive complexity, plus it really only works best at low Reynolds numbers, meaning slower fluid flows. So it is an amazing tool for specific high-end industrial applications, but it's definitely not a universal solution for consumer hardware.
That makes sense.
Yeah.
But carving the outside of the tube, or even electrifying it, is completely pointless if the inside of the tube is choked.
Yeah.
Because vapor condenses inside horizontal pipes too, right? And the environment in there is completely chaotic.
Oh, absolutely. Depending on the mass flux, which is the speed of the flow, and the quality, which is the ratio of vapor to liquid the flow inside the pipe, takes on completely different personalities. We call them flow regimes.
It's kind of like weather patterns inside a pipe.
That's exactly what it's like.
You start with stratified flow, where it's essentially a lazy river. Gravity cools all the liquid at the bottom, and the vapor lazily floats on top.
Right.
Then you speed up the mass flux, and you get wavy flow, where the vapor acts like wind, whipping up actual waves on the liquid pool. Go even faster, and you get annular flow. The vapor is moving so fast through the core of the tube that it shears the liquid into a perfect uniform ring against the entire inner wall of the pipe.
Yep.
And finally, mist flow, where the vapor just completely obliterates the liquid into a dense fog of droplets.
And looking at all these complex flow regime maps in the text from, Manthane or Teetle-Duckler or Solomon.
Do we really need to know the weather pattern inside the pipe, though? Like, why can't I just calculate the heat transfer at the beginning and the end of the heat exchanger and call it a day?
Well, this raises an important question, and it's actually a super common trap in early design phases. You cannot just use one overarching equation.
Why not?
Because the fundamental physics of the heat transfer totally change depending on the flow regime.
Oh, so?
Think about the stratified flow, your lazy river. The liquid is pooling at the bottom. The heat transfer there is driven purely by conduction through the thin film falling down the sides of the pipe, pulled by gravity.
Okay.
But in annular flow, you have a high-speed ring of liquid being dragged by violent vapor shear forces. That is forced convection. Conduction driven by gravity requires entirely different math than forced convection driven by vapor shear.
Oh, wow.
If you use a gravity-based Nusselt equation to predict an annular flow, your entire thermal design will just fail.
So you absolutely must know the weather inside the pipe to pick the right math.
You have to.
And the Teetle-Duckler map uses a really important parameter to predict when that transition from lazy river to annular ring actually happens, the modified Froude number.
Right. F sub Td equals the square root of rho sub g divided by the difference between rho sub L and rho sub g times gx divided by rho sub g times the square root of d times g times the cosine of alpha sub t.
Whoa. Okay, that is a massive alphabet soup.
Yeah.
If I'm staring at that on a whiteboard, what is the actual story it's trying to tell me?
Well, look past the individual symbols for a second and look at the physical structure of the math. It is essentially a ratio of two competing forces. Vapor inertia versus gravity.
Okay.
The gx term represents the vapor speed. It's forward inertia. The g term represents gravity pulling the liquid down to the bottom of the pipe. So when vapor speed increases, the top half of the ratio gets bigger. Inertia wins.
It's like a hurricane-force wind building up inside the pipe.
Yes. Until it is strong enough to physically pick the water up off the floor and plaster it against the walls, whipping it around the whole tube into that perfect ring of annular flow.
So it's a mathematical tipping point. If vapor inertia beats gravity, you're in annular flow.
Exactly.
So just like we added fins to the outside of the tube, engineers must have figured out how to rough up the inside to force the flow into these highly efficient forced convection regimes, right?
Sure, they did. And the most common method today is the microfin tube.
What exactly is an internal microfin? Are they like the sawteeth on the outside?
They are drastically smaller. We are talking about 30 to 80 tiny trapezoidal fins, just 0.1 to 0.25 millimeters high.
Oh, that is tiny.
Yeah, and they spiral down the inside of the tube, kind of like the rifling in a gun barrel.
Less than a quarter of a millimeter. How does something that microscopically small do anything to a roaring flow of refrigerant?
They act like microscopic speed bumps. They add just enough roughness to mix the flow right at the boundary wall, physically disrupting that insulating sublayer of liquid. And more importantly, even at that tiny scale, they still provide about 50% more surface area than a smooth tube.
That's brilliant. But,
Uh,
microfins are modern, high-tech manufacturing. The text brings up a historical artifact that I absolutely loved: twisted tapes.
oh, yeah.
Back in the 19th century, marine steam boilers on ships used literal twisted ribbons of metal. They call them retarders, and they just shoved them down inside the pipes to physically spin the flow.
And that 19th century trick is actually still incredibly relevant today. Twisted tapes force the fluid into a swirl flow, and the math used to model this, the swirl parameter, is surprisingly elegant.
Yeah, SW equals RE sub D divided by the square root of Y.
Right. RE sub D is the Reynolds number based on the tube diameter. It
Yeah.
essentially represents the flow's forward momentum, and Y is the twist ratio of the tape, basically, how tightly the ribbon is twisted. It perfectly models the physical intuition. Spinning the fluid increases the path length it has to travel through the pipe, but more importantly, it utilizes centrifugal force. The spinning motion physically throws the heavier, cooler liquid out against the heated wall, constantly mixing the fluid.
That is a brilliant way to correlate the complex physics of swirl flow into a single, highly usable variable.
It really is.
Okay, so what does this all mean? We've perfected the microphysics.
Yeah.
We've analyzed a single drop on a plate, the sharp tip of a single fin, the weather inside a single pipe. Let's zoom out. What happens when you stack 10,000 of these perfectly engineered tubes inside a massive power plant X-shell condenser? I'm guessing it isn't just 10,000 times better.
Right. If we connect this to the bigger picture, you are exactly right. It introduces macro chaos.
Macro chaos.
A single tube performs beautifully in a vacuum. A bundle of 10,000 tubes the size of a city bus creates a cascading series of nightmares for a plant engineer. I mean, a 2% drop in efficiency here means millions of dollars wasted on excess coal or nuclear fuel. And the two biggest threats to that efficiency are condensate inundation and non-condensable gases.
Condensate inundation. That sounds biblical.
Well, it is a flood. Remember how hard we worked to thin the liquid film off our single tube?
Yeah, below fins.
Well, in a massive bundle, gravity pulls that liquid off the top tubes, and it rains down directly onto the tubes below them.
Oh no, so the tubes at the bottom of the bundle are just getting drowned in an insulating waterfall of liquid from the thousands of tubes stacked above them.
Exactly. The thermal performance of the lower tubes completely plummets because their film thickness, is artificially massive.
Okay, and then you said the second nightmare was non-condensable gases. Stray air that inevitably leaks into the vacuum system.
Right.
I think of it like an air bubble trapped in your home plumbing. You turn on the faucet and it violently sputters because that pocket of air is completely blocking the flow of water.
That is a perfect visualization, and in a massive condenser, these air pockets don't just cause a sputter, they create massive thermal dead zones. Tinker made a really famous observation about this in 1933. In an X-shell condenser, the incoming vapor is channeled into different bays. Because the pressure must drop evenly across all the bays, but the tubes are warming up at different rates, the bays at the cold end of the condenser literally run out of steam.
Run out of steam? What do you mean?
The vapor all condenses before it even reaches the bottom of the cold end bay. So what fills that empty space at the bottom?
Non-condensable gases.
Exactly. Massive dead zones filled with trapped airform at the bottom of the heat exchanger, rendering hundreds of expensive, perfectly engineered tubes completely useless.
But you just vent the air out, right? Like put a vacuum pump on the bottom of the shell.
Well, proper venting is the solution, but
Yeah.
it creates a massive operational paradox.
Oh, so.
If you vent too little, the air pockets grow, choking your multi-million-dollar plant and tanking your thermal efficiency.
But if you vent too much, you're sucking valuable high-pressure steam right out of the condenser and venting it into the atmosphere.
Right. You are literally throwing away the very energy you're trying to capture. It's a terrifying balancing act.
It's crazy. It requires meticulous design. Engineers have to, orifice vent manifolds, meticulously cascading vapor from hot bays to cold bays, all just to manage invisible pockets of stray air.
It's intense.
It is wild how much invisible physics goes into a process we take for granted every time we see dew forming on a glass of ice water. We've gone from Nusselt analyzing a single vertical plate in 1916 to sculpting sawtooth fins at the microscopic level to cheat surface tension, to electrifying refrigerants to violently blast the film away.
We really covered some ground today.
We mapped out chaotic, hurricane-like weather regimes inside a single pipe and finally wrangled the massive cascading aerodynamics of a 10,000-tube power plant condenser.
It is a phenomenal journey through the scales of engineering, but, there is one final, really mind-bending fact hidden at the very end of the source material that I want to leave you with.
Oh, let's hear it.
We spent all this time talking about tubes, but what about plate heat exchangers? These are compact, brazed sheets of corrugated metal stacked tightly together.
Oh yeah, they are becoming huge in the modern HVAC industry because they are so compact and efficient.
Right. Well, Kazierski actually tested a plate heat exchanger acting as a condenser. It was installed vertically, as intended by the manufacturer, but then he simply took the entire unit and tilted it horizontally on its side.
Wait, he just knocked the whole unit over 90 degrees.
He tilted it 90 degrees, and by doing absolutely nothing else, the heat transfer performance was boosted by up to 30%.
30% just
Yeah.
from laying the plate on its side. But why?
Because of everything we've talked about today. By laying it horizontally, he radically shortened the vertical length that the liquid film had to travel.
Oh, I see.
Instead of flowing all the way down a long vertical plate, accumulating thickness and insulating the metal, the liquid only had to flow down the short width of the plate.
It prevented the film from ever getting thick.
Exactly. A thinner film means a smaller delta, which means a massive spike in heat transfer.
That is incredible. And it really makes me wonder, could the industrial condensers of the future abandon massive stationary tubes altogether? Like, could we use AI to dynamically tilt and rotate massive flat plate heat exchangers based on real-time fluid flow, constantly shifting their orientation to artificially cheat gravity and keep that condensate film perfectly thin?
It's definitely an engineering challenge waiting for a solution. The physics are entirely there.
Well, design junkies, that is a problem for you to solve. Thank you for joining us on this deep dive into Chapter 10. Stay curious, keep questioning the math, and we will see you next time.